Okay, this is the second in a series of videos talking about how to draw circumcenter, incenter, centroid, or orthocenter. These are called points of concurrency, and they're basically points of intersection of a triangle based on a particular original fold or line that you draw. And then they're kind of cool how it works out, but we'll see. All right, so I've already done the circumcenter, so now we're going to do something called the incenter. We're going to find the incenter. Now, the first thing we need to do to find the incenter is that we want to find the angle bisector. In other words, we want to be able to bisect the angle of a triangle, and if you bisect each angle of the triangle, there's 3 of them, they will actually intersect at something called the incenter. Those folds or those angle bisectors will all intersect in one spot. And when you intersect these dark lines at one spot, those are your angle bisectors, you'll end up with a point that is actually the same distance to each side of the triangle. And remember, when you're measuring from distance of the inside of a triangle or from a point to a line, any distance is always going to be measured in a perpendicular way because that's the shortest distance between the point and the side. So anyway, so that's kind of the special property of an incenter, is that it's actually the same distance to each side. Now, I just want to note that when we did a circumcenter, we bisected the sides and we got the same distance to each vertex. When we do an incenter, we're bisecting the angles, but we're getting the same distance to each side. Kind of cool. Anyway, all right, so let's start by talking about what an angle bisector is, okay? An angle bisector is basically dividing an angle into 2 congruent angles or 2 equal parts. Well, how are you going to do that, right? So if you wanted to make life harder for yourself, you could use a protractor and try to say, okay, well, this angle is, well, it's not a perfect angle, but it's maybe 61.5 degrees, and so I want to draw an angle that's half of that. Okay, but the way we do it if we have patty paper is that we can simply fold the patty paper. Now, the first thing you want to do is sort of make a fold right at the vertex, okay? Now, when you make a fold at the vertex, you don't want to fold it all the way because that's not going to bisect the angle. Because if you notice, the angle that's on top of the paper is a smaller angle than the angle on the bottom of the paper. If these 2 angles were congruent, they would overlap exactly. So basically what you're going to do is just kind of slide the patty paper around so that the left and right side of the angle overlap. And what that does is that the angle on top, this angle on top, and this angle on the bottom are the same angle. Well, that's what a bisector does. It divides it into 2 congruent angles. So when you do that, then you label it as such. We use dashed lines, and then we use what I call smiles. They're like the little markings to show that this angle and this angle are congruent. Now you're going to do the same thing to each angle of the triangle by folding it so that each side matches the other side. So what are we trying to do here? If we do 3 angle bisectors, where they intersect, where those folds intersect, will be called the incenter, and then that incenter will be the same distance to each side of the triangle. All right, so let's take a triangle and do it. All right, so we have a basic scalene acute triangle, and we're going to find 3 angle bisectors. It doesn't really matter which angle you start with, but let's start with angle B just because it's on the top. So you're going to fold it at angle B, but again, you want this BC, which is the one side of the angle. Just think of this as this angle. Don't worry about the bottom of the triangle. That means nothing. All we care about is that this side and this side overlap exactly. So you want BC side and BA side to overlap, but you want it to be folded at the vertex. So you fold it at the vertex, and you kind of look at the sides. We want the sides to overlap exactly, but be pinched at the vertex there. So we want it to be as close as possible, and then you make a nice little crease. All right, so there's your crease, and we made an angle bisector for angle B. Okay? And then we mark it with the smiles. Now let's do C. I'm not really going in order, but that's okay. So all we care about is angle C. We don't care about this side on the bottom. We just care about angle C. We want angle C to be bisected. And you can kind of get a feel, visualize for where that bisecting is going to occur. So you just sort of pinch it at the vertex there. And then again, you want the sides of the angle to overlap. We don't care about the bottom at all. So we want the sides of the angle to overlap so that the left side of the angle and the right side of the angle overlap, so that the CA and the CB overlap exactly at the vertex. So now we've made another angle bisector, and we'll mark that as such. And if your folds are nice and accurate, then it makes your incenter line up perfectly. If you're careless with your folds, then the three lines, the three folds that you do will not necessarily intersect at a point. It'll sort of be like a little mini triangle under there, and so that's not as good because you're not going to get an accurate incenter location. So again, we folded it at the vertex, and we want this angle on the top sheet of this patty paper and the angle on the bottom sheet of the patty paper to be the same angle. That's what bisecting means, so we want to be able to do that. All right, here's my green one. And so we will, sorry, it's getting caught on the fold here. Okay. And if you'll notice, my folds are pretty good, so they happen to intersect right here at this point. And we're going to mark it with our smiles. And so this point that we found is actually called the incenter. Now, what's special about the incenter is that we said it would be the same distance to each side in a perpendicular way. All right, so if we had something that was a perpendicular, like the edge of a piece of paper was perpendicular, and I've cut this one, so I don't know which edge is perpendicular, but I think it's this one. So if we were to measure the distance from the side of the triangle to the incenter, then that distance from here to here is that distance, whatever that is. And if we were to measure to the other side, from the side of the triangle to the incenter, that distance is about the same distance. And then the third side, the distance from the side to the incenter, again, is about the same distance, okay? So what do we mean by, why is it called incenter, and what does that mean? So basically, if we were to inscribe a circle in the center of the triangle such that the circle touched the edges, and I didn't do a perfect job here of using my compass, but if the circle were to touch the edges perfectly, the incenter is the same, is the center of the circle. So it means that this is the radius of the circle, because the radius is the center to any point on the circle. This is the radius of the circle, and this is the radius of the circle. So that means that if you were sitting at or standing at a triangular table and you all wanted to be able to reach something in the center of the table, like a bowl of chips or something, and you wanted to be the same distance to the chips, you would be, the chips would be at the incenter, and each of you guys would be standing or sitting at this part of the table so that you could reach that. So the incenter is the same distance to each side in a perpendicular way, but it's made by angle bisectors. So you might be asking, well, what happens if you have a right triangle, right? So we can inscribe a circle inside of a right triangle. And so the center of the circle that's inside the right triangle should be the same distance to each side. But let's look at our angle bisectors. So if we bisect angle B, all right, you got angle B, you want to overlap it exactly so that the left side and the right side of the angle overlap, and then intersect or find the bisector of angle C. And so we fold it like this. Okay, and then angle A is a right angle, so we're going to make two 45-degree angles here. And you do that, and my three folds, I'm not sure if you can see, but they intersect there, and the distance to each side of the triangle is congruent, okay? So then, what if you had an obtuse angle, the same triangle? The same thing happens. So I went ahead and inscribed the circle for you just so you could visualize what was happening. So angle A is here, and again, the angle bisector. It's a little harder to do angle bisectors of obtuse triangles just because they're so small. These base angles are so small. So you fold it so that the left side and the right side overlap, just like you did. Angle B is a little easier because it's obtuse. So you want the right side of the angle and the left side of the angle to overlap exactly. So when you go to do that, you slide the sides so that they overlap exactly, but still making sure that your fold is at the vertex. And then angle C, you're going to do the same thing. You fold it at the vertex, and you want the left and the right side of the triangle to overlap, so you slide it this way. Again, making sure that the sides overlap, but you're folded at the vertex. So those three folds will intersect at a point, and that point is called the incenter. And again, the distance from the circle to each side, the center of the circle to each side is the same. So that's how you make an incenter with patty paper, and you label it correctly. All right, stay tuned for the centroid.